Welcome back. Let's dive right into this explainer, brought to you by Forge College. Today, we're tackling the absolute culture shock of moving tokens on Solana compared to what you might be used to on the EVM. If you're coming from Ethereum, Solana's token mechanics can honestly feel completely alien at first. It's kind of like trying to drive a spaceship using a steering wheel. Now, in our previous lesson, we covered how metadata and token extensions work, but metadata doesn't just magically jump from wallet to wallet on its own, right? So today, we're focusing on the actual atomic workflows of moving assets. We're going to look at exactly where minting, accounts, and metadata intersect in real-world applications. So get comfortable, because we're about to fundamentally rewire how you think about token transfers. Here is our blueprint for today. We'll start with a welcome to SVM transfers, compare EVM versus Solana mechanics, map out the transfer workflow, build the transaction, cover handling transfer failures, and wrap up with some key takeaways.
Let's jump into Section 1, Welcome to SVM Transfers, or what I like to call the mailbox dilemma.
Sending tokens on Solana is way less like updating some magical global ledger and a lot more like delivering a physical package. Imagine you want to send your friend $10, but first, you literally have to pay the blockchain landlord to build them a wallet just to hold it. That's the reality of the Associated Token Account, or ATA. Every single token mint requires a dedicated on-chain mailbox for every single user. You can't just fire a token at a user's main wallet address, you are actually sending it to their specific ATA for that specific token. And because this takes up physical data space on the network, it costs rent, paid in Lamports, just to keep it there.
And hey, before we write any code, I want to give a quick shout out to Forge College for making this explainer possible. Make sure you visit forge.college later to level up your Web3 skills. Mastering these atomic transfer mechanics is exactly the kind of practical leverage you absolutely need to build robust, decentralized apps. Moving right along to Section 2, EVM versus Solana mechanics, ledger versus accounts.
What's really fascinating here is how radically different the core philosophy is. On the EVM side, you basically tell a giant, all-knowing smart contract to just shuffle numbers around in its internal ledger. The person receiving the tokens doesn't have to lift a finger to prepare for it. But on Solana, the token program is completely stateless. The data, meaning the balances and the mint references, they live in completely separate, distinct ATA accounts. You literally have to explicitly move data between them.
This contrast is brilliantly illustrated when we look at the specifics. Notice how on Solana the burden of ensuring account readiness and paying the rent for new storage falls squarely on the person paying for the transaction. Look closely at the readiness and fees here. On the EVM, no setup is needed at all. But on Solana, if the recipient doesn't have that specific token yet, they don't have the ATA, which means your transfer will literally just bounce off the network and fail because there's nowhere to put the tokens. And if you have to create that account for them, well, someone, usually you, the payer, has to explicitly fund the creation of the recipient's brand new mailbox. All right, let's get into Section 3, the transfer workflow, our blueprint for success.
So if the recipient having an ATA is a strict precondition, how on earth do we build marketplaces or airdrops without throwing constant errors? Well, we solve this by building the mailbox while we deliver the package. Here is our precise 5-step atomic workflow. First, you do a pre-flight check. You use the recipient's public key and the token mint to calculate what their ATA address should be, and then query the network to see if it even exists. Second, you check your own source balance. Third, if their ATA doesn't exist, you build a transaction that groups an ATA creation instruction together with the actual transfer instruction. Fourth, you submit it all to the network. And fifth, you plan for things to go wrong.
Which brings us to Section 4, building the transaction, where we translate this into TypeScript.
It's actually incredibly satisfying to see how elegantly Solana's Web3.js handles this conceptual blueprint. You dynamically inspect the network, right? And if the ATA is missing, you just append a creation instruction right before the transfer checked instruction. It all gets packaged into one atomic bubble. You basically start with an empty transaction, check if the account exists, and if it doesn't, you push the creation instruction in. Then, right behind it, you push the transfer instruction. Finally, you just need 2 signatures. The payer signs to fund the rent for the new ATA, and the source owner signs to authorize the actual debit of the tokens.
I really want to highlight the number 0 here, because whether you're sending fungible tokens or a single NFT with 0 decimals, transfer checked strictly validates this number to prevent absolutely catastrophic unit conversion mistakes. Unlike a basic transfer instruction, transfer checked forces you to explicitly declare the token decimals. If you're moving an NFT, the amount is 1 and the decimals are 0. Moving a stablecoin, it might be 6 decimals. If your application logic gets confused and tries to send the wrong decimal amount, the runtime will reject the transaction entirely. It's a vital safety net. Let's move on to Section 5, handling transfer failures, or what to do when things go wrong. Because let's face it, in the real world of dApps, things do not always go smoothly. You've got fluctuating RPC nodes, users with empty wallets, network congestion, the works. So you might be wondering, if we create the ATA, but the transfer part fails halfway through, do we leave the system in some weird, broken state? Since we're grouping two distinct actions into one request, what if the recipient gets a shiny new mailbox, but your tokens never actually leave your wallet? Thankfully, because we grouped everything into a single atomic transaction, a failure means the whole thing reverts. It keeps everything perfectly safe. This is honestly the beauty of the Solana runtime. It treats your bundled transaction as a single unit of work. If the pair doesn't have enough LAM ports to fund the ATA creation, the whole transaction fails. If the ATA is created but the source account lacks the tokens for the transfer fails, which triggers a complete reversion. The ATA creation is magically undone, and the network state remains perfectly clean. No partial state ever. When you're debugging, you're going to want to keep an eye out for a few specific failures. And always design your clients to use idempotent retries so you can safely try the transaction again. If you see an account not found during a transfer, it means your pre-flight check failed or you just forgot to append the creation instruction. An instruction error.custom usually means an insufficient token balance. And because your transactions are atomic, you can design your front end to just say, oops, let's try that again, without worrying about accidentally duplicating a transfer or paying for a mailbox twice. If a transfer fails due to a timeout, your next pre-flight check simply sees the ATA already exists and only sends the transfer instruction the second time around.
Let's wrap this up with Section 6, Key Takeaways.
Let's distill everything we've covered today into the absolute core rules you need to memorize. Remember these 5 principles, and you're going to have a robust, repeatable transfer pattern suitable for wallets, marketplaces, and really complex back-end services. Number 1, never assume a recipient is ready to receive a token. 2, always perform your pre-flight account existence checks. 3, bundle your ATA creation and transfers to ensure atomicity. 4, protect yourself from unit errors by relying on transfer checked. And 5, always build your apps to use idempotent retries for error recovery. So now that you've mastered transfers, how do we encapsulate this into audited on-chain workflows? And if Solana gives us this much granular atomic control over state, what does that actually mean for the future of complex DeFi composability? We are going to answer exactly that in our next lesson, Why Solana Uses Reusable Programs, where we'll explore cross-program invocations. Once again, this explainer was brought to you by Forge College. Be sure to check out forge.college for more Web3 deep dives. Thanks so much for joining, and keep building.